Welcome to the lecture series called Introduction to MEMS. MEMS stands for Micro-Electromechanical Systems. My name is Chang Liu. I have been a professor, a researcher in the MEMS field. I have been in the industry of MEMS and have led startups in this field. And in this lecture series, we're going to talk about a number of things. First, I'll give an introduction about MEMS. uh, because MEMS and semiconductor chips are very much related. So I'll discuss why the semiconductor material is important. I'll give an overview of the chip industry, and I'll also talk about the facilities called cleanroom and their cost today. After this, I will spend a few lectures talking about semiconductor process. I'll first give an overview, then discuss micromachining processes related to making micromechanical structures. I will do a deeper dive into how people make three-dimensional MEMS devices, including wet etching and gas phase etching. After this, I'll talk about MEMS transducers, including sensors and actuators, and give a foundational overview about mechanics. I'll then discuss the quality control and integration yield for MEMS processes. The last few lectures is related to uh, the interface of MEMS and industry. I'll talk about MEMS startups and lessons learned, as well as the art of managing a company to lead in the innovation and success. Now let's proceed to the first part of the lecture series, Introduction to MEMS. I'll give a brief history about the evolution of the field. In 1959, there was a famous talk by Professor Richard Feynman at Caltech. The title is There's Plenty of Room at the Bottom. In this talk, Dr. Feynman discussed a future where micro and nanoscale machines are going to be made with very refined fabrication technique. Mind you, at that time, all these techniques to make this small and nano machines have not been made available yet. The history of semiconductor and MEMS is actually very long. It started with scientific research in the solid-state device physics field. Around 1940s, AT&T Bell Labs have started to make transistors, switches. They want to make better and smaller switches for telephone switching. And this led to the invention of the transistor. And in 1968, the companies like Intel and Texas Instruments have started to make planar integration of circuits, what they call VLSI, very large scale integrated circuits. The VLSI devices led to the creation of memory devices, logic devices, and CPUs. For about 2 to 3 decades, the growth of the field followed what's called the Moore's Law, which predicted very early on that the density of device integration would double every 1.5 years. This trend actually lasted for a few decades, and this leads to the creation of personal computing, internet, mobile internet, 5G, and now AI. Now, people have been concerned about the future of the Moore's Law for a long time. Around 2020, it was finally realized that the Moore's Law may have to end because the line width resolution is approaching 10 nanometers. But what I think surprised a lot of people is actually the Moore's Law actually continued in a different dimension. And this is called the post-Moore's era. In this era, the chips are integrated in a chiplet fashion, like building Legos into a system on chip SoC. And actually, the integrated circuit field becomes ever more exciting. In 2025, for example, TSMC, Taiwan Semiconductor Microelectronics Corp, leads a pack of foundries, and this includes Samsung and Intel, which are fighting fiercely. A company called OpenAI leads the GPT field, and they use chips made by NVIDIA. NVIDIA actually becomes the first company to reach 4 trillion valuation because all this large language model training and generative AI use resulted in very heated use of their chips. In modern colleges, there are many majors: electrical engineering, mechanical engineering, and so on. But the MEMS practitioner needs to be a little different. They need to wear many hats. A MEMS practitioner needs to be a mechanical engineer and an electrical engineer. He or she needs to know something about semiconductor process and semiconductor device physics. They are physicists, they are chemists, because they need to know the processing chemistry. And ideally, they should be hands-on so that they can have first-hand experience. And they need to have analytical skills to do failure analysis of devices and processes. A really successful MEMS practitioner, I mean a really, really successful one, ideally should also have entrepreneurial skills and is a CEO material. This would allow your inventive ideas to go a lot further. Now, what are MEMS used for? I'll give you a few examples. Fortunately, what has made the MEMS field prosper is that there are many high volume applications that requires sensors or actuators. Here's one example: MEMS microphones. MEMS microphones are used in cell phones in many, many different capacities. Using micro machined devices, you can make the microphone really, really small. They can fit into many small devices, and their price can be really low. So this is really important. Another example is MEMS tire pressure sensor, or TPS. I have to be honest that in 20 years earlier time, I wouldn't have imagined that the TPS becomes so big. Nowadays, you can find MEMS pressure sensors in almost every new cars, and you can look at the actual pressure inside a tire. And the sensor is made of a silicon. The silicon have a diaphragm, and the diaphragm contains piezo resistors made by doping silicon. When you have pressure changes, then the displacement of the membrane would cause the piezo resistors to change its value. And this allows the pressure to be actively measured. Modern electronics have allowed wireless communication between the sensor and the car itself using Bluetooth wireless. This is a very important improvement compared to the uh, sensors that would be done otherwise. Traditional sensors are made by, for example, microfabrication of smaller parts, but the smaller parts are never micro. For example, you can make a sheet metal canister that can collapse when the pressure changes, and this can cause the dial on the pressure reading to change. But this device can never be used for the uh, tire pressure measurement as we're using it today. When you go to movie theaters today, you might be in one that has a laser projector. The laser projector, for example, at AMC, uses 3 colors of laser, and the laser lights are mixed together and projected onto the screen through a DMD chip, digital micro devices. The DMD chip is a MEMS chip that employs thousands of micro mirrors that forms a high resolution images on the screen. So I hope that you're convinced that MEMS have many big and important applications everywhere in our life today.